from Bharati Darshan University in 1987. He worked for Indian Space Research Organization briefly. He received MASc Engineering and PhD from Department of Electrical and Computer Engineering from University of Toronto, Canada in 1993 and 97 respectively. He joined the IIT Delhi as a lecturer in 1997, where he is currently serving as a professor in the Department of Electrical Engineering. Dr. Shankar Prakriya was associated faculty with Bharati School of Telecom Technology and Management at IIT Delhi until February 28, 2018. He held the Jay Gupta Research Chair for 5 years until 2017. He held 2 US, Korean, Japanese, Chinese patents related to DSL and 1 US patent on wireless communication. He has filed several patent applications related to 5G communication. Since July 2021, he is serving as an editor of IEEE Transaction on Wireless Communication and senior members of IEEE. On behalf of whole organizing committee, I welcome you, sir. So over to you, sir. Sir, you can start, sir.
Okay. Thank you very much for your kind introduction. Let me try to share my screen.
Yeah, it's visible, sir.
Oh, okay. Yeah, it's not visible to me, so I was wondering what happened to this thing. Okay. 1 second, please.
Okay.
How do I make it visible to me? I hope you're able to see the screen now.
Yes, yes. But your PPT is not visible, sir.
No problem. Yeah. Now it's okay.
Still, it is not visible, sir. Showing double click to enter schools.
You're not able to see the screen still?
It's no, sir. We can't able to see. It's
Okay.
a black screen.
Sorry for that. Okay. Are you able to see it now?
No, sir.
No, sir.
Oh, what's happened?
You stop sharing and start again.
Yeah, I think I have to do that. Yes. Oh, share.
Sir, it's difficult, sir. Sir, I'm just in a meeting.
Okay, I don't know what's happened here. Stop share. Are you able to see the screen now?
But it is showing started sharing the screen, double click to enter full screen mode. So it's a blank screen it is showing, sir. This screen is blank.
Oh. I'm sorry for this. You have to.
Fine, sir. No problem. The PPT is, I think it's not. It's before doing full screen, just see the only PPT, whether it is visible or not.
I don't understand.
Sir, I just try to share my screen.
Mhm.
Check either it is any network issue.
Okay.
One minute, sir. So, are you able to see that screen, my screen?
Yeah, I'm able to see, yes.
So, network is perfectly right. So, you can check your answer.
So, sir, you just again rejoin, sir. You can.
You can rejoin, sir.
Okay, I'll do that. Okay. I'll leave and rejoin. Because it was absolutely fine just a while back. It says host has disabled screen sharing. Please enable it again for me.
Yeah. So, sir, you join some other names, sir. It's like.
No, 1 second, hold on. I had to change the name also here. Wait, I don't know.
Yes, yeah. Yes, sir. You now try to share your screen. Yeah, sir. We can able to see. Yeah.
Oh, thank you. Okay, welcome all of you. Thank you very much for your kind introduction. I'm sorry for the interruptions. I think there was some software issue from my side, perhaps. So I'm very happy to join this international conference on artificial intelligence and signal processing at VIT. So I will be speaking on non-orthogonal multiple access for massive machine type communication and the importance of learning in this context. Right? So my research interests are broadly in the area of non-orthogonal multiple access, massive machine type communications. I have in the past worked on interference management, D2D communication, full duplex relay. Also worked a little bit on battery energy management and IoT devices. We have a patent which is now granted in US. And cognitive radio, buffer relaying, energy harvesting, backscatter. And more recently on intelligent reflecting surfaces and so on. Right? So, of course, well, this is my recent work, as you can see, on relates to energy harvesting. Also, some recent more work related to energy harvesting. short of time, but yeah, they also worked a little bit on energy harvesting with buffers. So some of these have appeared here. Then some more, I think, yeah, so hold on. Yeah. And cognitive radio, I'd worked in the past in a Media Labs Asia project. So there's some, all these have appeared in 2019, 2017, so on, cognitive radio. I also worked a little bit on full duplex communication with a research scholar. Also in context of non-orthogonal multiple access, you can see. More recent work on non-orthogonal multiple access. I'll be discussing some of these. We proposed a user selection scheme which gives higher diversity. This appeared quite some time back, 2018. And okay. And also worked on underlay, NOMA and underlay networks. Maybe I'll briefly touch upon this a little bit. We also worked on coordinated direct AFDF relay aided NOMA for low outage. It had just appeared in transactions and communications, still in early access. Interference management I worked in the past. So it gives you a brief idea of my work and work of my students. Basically, it has been centered around performance analysis of wireless communication systems. Very certainly, I'm not an artificial intelligence or machine learning expert, but because I have been working with massive machine type communication, I do appreciate the importance of machine learning, and that I thought I would bring out through this talk today. Right. So this figure I had picked up from one tutorial article on 6G. It shows the evolution from 1G to 6G. As you can see, basically from voice. In 2G, you move to text and voice. In 3G, you move to multimedia and voice, and so on. So in 4G, I think we're all broadly familiar, right? The type of things that are possible with 4G. And in 5G, of course, we have wearable devices, smart cities because of IoT and the ability to have grant-free access and so on. Yeah, and telemedicine. And 6G, they're contemplating something fundamentally different. They're talking about tactile internet, fully automated cars, holographic verticals, and so on, as you can see. And regarding the KPIs, you can see that it has been changing dramatically. If you look at the peak data rates, in 6G, you're expecting a peak data rate of greater than 1 terabit per second. That's an enormous amount of speed. Even the 5G speed of 20 gigabit per second is very, very high. Right? So, but you can see the orders of magnitude increase in the peak data rate. And also in the mobility, right? In the case of 1G to even in the case of 5G, you're looking at 500 kilometers per hour of high-speed train travel. In the case of 6G, you're looking at 1,000 kilometers per hour of mobility. Extraordinarily low latency, as you can see. Right? We're talking about 10 to 100 microseconds latency in 6G and 1 milliseconds in 5G, which is very, very ambitious. And if you look at devices per square kilometer, maybe that is where the real story is. The number of devices per square kilometer was very, very small in 1G and 2G. It is increasing dramatically and order by orders of magnitude. And you're expecting around 10 power 7, about 10 million devices per square kilometer at the very minimum in 6G. Right? This is a very large number of devices. Most of these are machine type devices. And this is where the real story lies, right? And we're going to talk about it. And of course, the amount of megabit per second per meter square also increased dramatically. That means there's going to be high density of traffic. And spectral efficiency you're looking for is enormous. You're looking at 15 times the spectral efficiency of the earlier schemes. Right? That is pretty good. Basically, it's been compared to 4G. As compared to 4G, it's 15 times at least. And energy efficiencies they're looking for are enormous. They're looking at 100 times the energy efficiency of 4G. So these are very interesting numbers. And of course, there is also network characteristics. The nature of the network traffic has changed from purely voice to packet switching, circuit switching, and so on. I think these are all of us are broadly familiar. But in 6G, machine learning intelligence is going to play a very important role. Softwareization, virtualization is going to play a very, very important role. So as you can see, the type of technologies Of course, earlier we were used to GSM and GPRS. Then we went to 3G to WCDMA and so on. We tried CDMA. And then, of course, in 4G, we tried various types of technologies that came into the picture. D2D, for example, for the first time. MIMO, carrier aggregation, these ideas came in. 5G, of course, all of these we are familiar. Non-orthogonal multiple access first came in some form in 4G, but in 5G it appeared to be used. It's to be used to much larger scale. Millimeter wave communication. But in 6G, the type of things people are talking about are very different. We're talking about quantum communication, terahertz communication, and you're looking at artificial intelligence and RIS, reconfigurable intelligent reflecting surfaces. We'll see that a little bit later. So the story seems to be that there's going to be a dramatic increase in number of devices per square kilometer on orders of magnitude higher data rates. And volume of traffic per square kilometer is going to be much, much larger and orders of magnitude low latency. This summarizes the previous slides. And ultra low power consumption at network level and also at the node level, because you're looking at nodes, which are machine type devices, you're expecting them to have extraordinary long battery lives. So you're expecting very high level of node level energy efficiencies. So in order to cater to such a large number of devices, you cannot have, definitely we cannot use orthogonal multiple access. Conventionally, you have base stations today that talk to each device individually, right? You allocate a resource block and you communicate to one particular device. Right? And similarly in the uplink, right? So for such a thing, we cannot afford to do so anymore because there are going to be 10 million devices per square kilometer. It is not possible to allocate orthogonal resources to each of these devices, either in time or frequency or code, whatever. So it is not going to be possible, which means that we have to go for non-orthogonal multiple access. Okay? And also orthogonal multiple access, as it is called, whatever has been traditionally used, cannot meet your latency requirement for sure. Right? You need to have, for example, in the uplink, you need to have devices communicating with very low latency to the access point. That is not going to be possible orthogonal multiple access when there are going to be 10 million devices per square kilometer or more, right? So signaling overheads become very large. This also is a very major issue, right? Because when you want to talk to any particular device, either in the downlink or in the uplink, there is some kind of protocol to be followed. There is a request to send data, and then the request is granted, you transmit data, you wait for an acknowledgement and so on, right? And the resource block is allocated to you and then you transmit and then you wait for an acknowledgement. Right? But such type of signaling overheads are simply not possible when the number of devices blows up like this and becomes so very large. You're going to have something called grant-free access, which means that devices will simply shoot data whenever the data is available, right? And without waiting for an okay from the access point. Right? This makes communication much more complicated. Right? So we're going to discuss that briefly very soon. Basically, non-orthogonal multiple access is what it's going to amount to. Right? And we need to have sophisticated interference cancellation techniques in order to decode all these data from these devices. Okay. So non-orthogonal multiple access has been known by many different names, maybe because many different companies were started. These basic ideas came from different sources. They have been using different abbreviations. Earlier it was called multi-user superposition transmission and so on. And depending on the company that was pushing it, right? And finally it was accepted in December 2015. So all kinds of abbreviations being used, as you can see. So what is the basic idea of power domain NOMA, the specific type of non-orthogonal multiple access that we're going to talk about? Right? So the basic idea is that, let us consider the downlink, right? We're talking about the base station of the access point transmitting to a cell center user, who is called the near user, and a cell edge user. Basically, you're trying to communicate to one strong user and one weak user in the downlink simultaneously, right? At the same, you're using the same resource block, right? And you're not using different codes or different frequencies and different time instant. Using the same time instant, everything the same, but you're going to multiplex in power domain. which is rather unusual and unexpected, right? Its frequency is the same. There are two users, user N and user M. As you can see, more power is allocated to user M than user N because user M is very far away. This is the far user. This person is far away from the base station, so is allocated more power, and less power is allocated to user who's close by. Right? So basically what you're going to do is you're going to transmit a weighted sum of symbols. Right? A superposition of symbols is transmitted, and the far user treats, which has got more power allocated to its symbols, treats the near user symbols as noise or interference and decodes. The near user, on the other hand, has to decode the far user symbols first because that has got higher power allocated, cancel the interference, and then decode its own symbols. As you can see, the near user signal processing has got increased, and it is going to incur certain loss in performance because of the fact it is cooperating in its non-orthogonal multiplexing scheme. But by multiplexing users in power, we're able to use the same resource block in order to communicate to one near and one far user, with the added with some disadvantage that you have to use more sophisticated signal processing at the near user. Right? Because you've got to get a weighted sum of symbols. When you get a weighted sum of symbols, either you have to use a multi-user detector of some kind, or you use simpler type of things like successive interference cancellation receivers. Right? You first estimate one is a stronger symbol, assuming the other one is weaker one is noise with interference, and then decode the symbol, cancel the interference, and then decode the weaker one. Right? This is the basic underlying principle. Now, what motivates non-orthogonal multiple access? It's a very simple idea, right? Look at this capacity equation. Capacity is bandwidth into log to the base 2 of 1 plus SNR, right? This bandwidth W appears in two places in the capacity equation, but one is a multiplicative factor, and one term which are not indicated here explicitly, but it comes in the noise term, because when your bandwidth increases, more amount of noise enters the system because noise is white, right? As the bandwidth increases, more noise enters the system. Therefore, the signal to noise ratio will degrade, right? But this is not important. What is important is a multiplicative term because the rest of it is within the logarithm, right? This is and the power term that you have is inside the logarithm, right? This is very critical idea, right? So bandwidth therefore plays a much stronger role. So what you need to do, so traditionally what has been done in OMA transmission, either we multiplex in time or multiplex in frequency. Here what the idea being suggested is that you have near user allocated half the bandwidth, far user allocated half the bandwidth, and you are transmitting to both the users. You'll notice then that a factor of half immediately comes in the capacity equation, greatly limiting the capacity attained by the near user and the far user. Right? The reason is that W is a multiplicated term. Dividing the bandwidth between two users is not a very smart thing to do. Whereas dividing the power is a smart thing to do because you'll be using the entire bandwidth for both the users, right? So W multiplicative term is full, and there is a certain loss in terms of power because you're going to have power apportioned between the near user and the far user. But power appears within the logarithm, so it is not a big deal, right? It can be managed. If you want to look at the equations, I don't think it is extremely important, but you can see that the capacity R1, R2, the rates attained. So you can see a multiplicative factor of beta and 1 minus beta, assuming that beta is the fraction of the bandwidth allocated to the near and far. I'm not assuming equal bandwidth to near and the far in OMA. I'm assuming that beta and 1 minus beta. And then we're talking about power being used. Let us call it P1, and we look at the signal to noise ratio. Obviously, the noise term also has a beta and 1 minus beta because bandwidth has changed. Right? You can write down similar expressions for non-orthogonal multiple access. If you look, HSF is the channel between the source and the far user, and HSN is the channel between the source and the near user. As you can see, first you decode the far user symbol at the near user, treating the near user symbols as noise. That is why you have this P1 and P2, because you're apportioning the power, right? With the understanding that P1 plus P2 is equal to the overall power P. Okay. And after it's cancelled, you decode only the near user symbols with which interference has been cancelled. So if you look at the capacity equation, the regions, assuming of course deterministic H, in this particular, and we can see that the regions attained by OMA are like this, orthogonal multiplexes. The regions attained by non-orthogonal multiplexes are like this, which is what makes non-orthogonal multiplexes so very attractive. Right? This figure is extracted from one survey. So multi-user NOMA, you do transmissions in the downlink. In one single resource block, you transmit to multiple users in the downlink. Therefore, you're able to communicate and transmit data to a large number of users. This becomes important. And similarly, also in uplink, you have more than one user is going to transmit concurrently at the same time using the same resource block in the uplink. And this is important because the number of devices is becoming very, very large. Right? So somebody has to decide which user is going to transmit concurrently, which set of users is going to transmit concurrently, right? In the downlink, you have to say some are near users, you call these as far users. Somebody has to do the separation and call this as near and far. Somebody has to group this user one with this user because this near user and this far user are grouped together and you transmit data concurrently to both of them, right? But somebody has to do this grouping. Somebody has to separate the near and the far users. Classification. These things are more complicated than it looks, right? But in a practical scenario. So, one other thing that we need to discuss is comparative NOMA. The underlying principle being that the near user helps a far user. Let me show the figure directly. There are near users here, and there's a far user here. One near user is picked, one far user is picked, and you are transmitting data from you transmit a weighted sum of symbols. The near user will decode the far user symbols and then decode its own symbol. This will decode its own symbols directly, right? But what you're doing in addition is asking the near user to relay the far user symbols which it has decoded to the far user, which is beneficial when this link is very, very weak. This allows enormously much better performance to be attained, right? Basically, what you're doing, you're allowing you're relaying by the near user, because the near user would have decoded the far user symbols. It makes sense to ask it to relay the far user symbols to the far user, because the signal to noise ratio of this link, SNR of this link, will be very, very good as compared to this link because of the distance. So various types of mechanisms have been suggested for picking users. One is called the best near, best far, and so on. And we proposed a slightly different technique. Let us skip these in the interest of time. We proposed a different technique. What we said is that let us pick one far user has got the best link SNR, right? Then what we do, from the far user, we pick the near user, which is able to decode both the symbols, near and far, and which has got best channel to the selected far user. Right? By doing so, we're able to attain a diversity. If the number of near users is n and the number of far users is f, we're able to attain a diversity of n plus f at the far user and n at the near user. And because we switch from OMA to NOMA, we're also able to ensure that the performance of the near user is not degraded in any way. And you're able to attain very good diversity here, which is very important because this user has very poor performance. Right? So attaining higher diversity is very, very important. This appeared in a letter item many years back, to 2018, I think. Okay. Sorry. I will skip these details. So as you can see, this outage, if you're interested, you can see. A traditional scheme gives lower diversity. The scheme that we have suggested gives a diversity of n plus f at the far user, which is enormous amount of improvement in outage for the distant user, which is a massive advantage, right? So I will skip some, and you can also see the power allocation, etc., has to be within a certain range. Certain very small power allocations are not applicable, and you cannot do non-orthogonal multiplexes with some power allocation between the near and the far. It has to be within a certain range, as you can see. But in this region, there is no throughput at all. Afterwards, you have non-orthogonal multiplexes and you have some throughput. And of course, when alpha becomes 1, you're allocating all the power to one user, and therefore the throughput will again degrade. Right? That is what we see. This is a matter of detail, but what I want to come to is the deep learning type of problems and why they are important. Let us come to that. But before I go to that, you see the cognitive radio, there are many types of NOMA being talked about. Terminology also can be pretty confusing sometimes. But you have cognitive radio inspired NOMA, where you treat the far user as a secondary system and try as the primary system and try to protect its performance and try to maximize the performance of the near user. So there are this kind of terminology being used. It's not actually cognitive radio, but you're using cognitive radio principles. There's MIMO NOMA, there is, NOMA is also being used in D2D, and so on. NOMA is also being used in context with simultaneous wireless information and power transfer, and so on. There's also this relayed NOMA framework for those of you who are interested. So there's a base station, you have a relay station, and the relay station communicates to one near user and the far user. So you communicate from here to here, you transmit a weighted sum of symbols, the relay decodes both, and then it transmits one more weighted sum of symbols, which is decoded by the near user and the far user. The near user employs SIC, successive interference cancellation. I'll skip this. This relates to coordinated direct and relay transmission, which I think what we're trying to do here is that we have a relay. We're trying to communicate to a far user and try to improve its performance. We have a direct link to both the far user and the near user. As you can see, this is also a relay. The relay is assisting communications, right? For those of you who understand cooperative communication, wireless communication, will see that normally, suppose this user was not there, you transmit to a relay, and the relay transmits to the far user, and the far user therefore gets two copies, one from here, one from here. One from the base station, one from the relay, and therefore gets higher signal to noise ratio. So what people suggested is that the relay can transmit the far user symbols. It seems to be good because then the far user, which is for distant user, gets better SNR. Right? What we suggested is that let the relay transmit a weighted sum of symbols, both the near and the far once again. Then we'll try to improve this. At the same time, we'll also improve the near user performance, right? Earlier, what is happening is that this gets a diversity of 2, but this was getting a diversity only of 1. So we said that let us transmit a weighted sum of symbols. While doing SIC, you combine both these signals and get a diversity of 2. So we're able to get a diversity of 2 at the near as well as the far. And when improving this performance, the power allocated to the near user can decrease, and therefore more power is allocated to the far user. Therefore, the far user performance again improves. Right? It is sort of counterintuitive, but it works. And we have shown this work just appeared in TCOM recently. We analyzed for relay being AF as well as DF. I will not bother you with the details. These plots, if those are interested, can go through the papers and see. Right? We're able to show diversity gain. You can see increased slope is what it is all about. So getting higher diversity performance of the near user is what we achieved. And recently, we also had some work in underlay systems, right? I hope you are able to understand, those of you who understand underlay cognitive radio networks, right? So what you do there is that you have a secondary base station. These are all secondary nodes. This is a primary node. They're using the same spectrum. When you transmit, secondary nodes have to make sure that the interference they cause to the primary user is below a threshold. Right? So this is transmitting. It's trying to make sure that the interference here is, let us say, a certain value I, which means that the power with which you transmit is a random quantity and it is limited. So in this power limited scenario, it is not very clear that NOMA will work. What we showed is that NOMA can still work provided it is made adaptive and it can be made to perform exceedingly well. Right? This work also appeared. It is sort of counterintuitive, right? Why would you do power domain NOMA when the power available with you is limited, right? But we are exploited the fact that the power is a random quantity. to switch between NOMA and OMA intelligently and we do user selection so as to get very good performance with NOMA. Right? This is what we achieved. This work also appeared recently. Okay, we'll skip the figures. We also have a look at secondary uplink transmissions. And so there are multiple users here. 2 of them are selected to transmit in the uplink. And they're also underlacing network. So interference that you have caused here has to be below a certain threshold. This interference is apportioned between these 2. So the power has to be carefully selected. We use knowledge of the channels and the interference that you can tolerate and try to select 2 users to transmit an uplink and show that much better spectral efficiency can be attained. More recently, we also worked on massive machine type communication. In this particular scenario, we have large number of users that are transmitting the uplink. We have a large number of IoT also transmitting the uplink. And what we're trying to do is, while one uplink user is transmitting, we're allowing grant-free access at a couple of IoT nodes. Right? They're using the same spectrum. What we suggested was a semi-grant access scheme. That means then it is not totally grant-free, which means that users, IoT devices cannot simply shoot data. And only more than one IoT node is selected in order to transmit data in the uplink, while the uplink selected user is transmitting. Right? So this work also applied for a patent for this. Okay, now let us look at non-orthogonal multiple access. In non-orthogonal multiple access, you have a superposition of symbols, right? Consider the uplink. Multiple users are transmitting with power Pk, right? The capital K users. Power is Pk, channel is Hk, and symbol is Sk. So you're going to get a weighted sum of these. You're going to get a sum of all these signals at the access point, right? And with additive noise. So what is the conventional approach? We can use multi-user detection. Right? Many types of multi-user detection techniques exist, right? And I think some of you might be familiar with these, right? And there is, of course, the successive interference cancellation, which is well motivated in NOMA, right? People do that. What they do is they control the power that each one user is using and make sure that the powers are carefully selected so that one user at a time is decoded, the interference cancelled, and then you can decode the rest. This is also a parallel interference cancellation technique. Now, one of the things that you can possibly do, suppose this alphabet size is S, right? You can treat this as a classification problem. Multi-user detection can be treated as a classification problem. Suppose the SKs are all binary, right? Then there are capital K of them. So there are 2 power K possible classes, and you are trying to select one among those, right? So it's a classification problem. And we know that machine learning, these deep learning techniques can be used in order to do such a classification, right? I hope you're able to understand what is going on. We're going to get a weighted sum of symbols. If this is binary, SK is binary, then there'll be 2 power K possible classes. And we're having classification problem, right? And if the alphabet size is S, there are S power K, which is very, very large. So it is not going to be easy, especially when alphabet size is large or capital K, the number of users is very, very large. But look at this particular situation, right? So we have a NOMA signal. This is an example with 2 users, right? We have an input layer. We have a hidden layer. We have an output layer to give 2, right? But treating it as a classification problem, we're able to use DNNs in order to perform this detection, right? But very large amount of training is required because the number of classes generally is very, very large. Here, of course, there are only 2. That can be very, very large. So, but this is something called the data-based model. We can also have more intelligent models based on the structure that is underneath, right, in NOMA. What we can do is can have some kind of a we have an input, we have separate branches for different outputs. So suppose you have two outputs, you have two branches. In this example, what you do is you have one hidden layer, one input layer, hidden layer, and then output layer. This output is fed back to this, and you cancel it, right? And when you do training, these coefficients that the weights that you use in each of these layers, it gets automatically picked, and you're able to select, get the two outputs. So to do SIC using DNNs is very practical and meaningful. It can be trained. The DNN can be trained in order to perform SIC. The advantage of this structure over the other structure should be very obvious to you. Definitely the number of weights that you need here is very, very small as compared to the weights that you require in the scheme, because the number of users, you have S power K sets here. It becomes very, very large. Here you don't have that large number of sets because each of these DNNs is smaller number of weights. And you're performing cancellation. You're exploiting the structure that is present in the problem, right? I hope you're able to see that non-orthogonal multiple access, you can do multi-user detection, or you can perform have receivers that based on DNNs. Similarly, here is a structure based on the parallel interference cancellation technique. You have the weighted sum of symbols, then you have the input layer, then you have different branches here, and you are having message passing between the branches. By having message passing between the branches, you're basically able to perform parallel interference cancellation, right? Obviously, these structures require much less training than the original DNN, which was database that you are just performing blindly, right? So these model motivated DNNs are of low complexity and they require much less training. So, okay. Now let's look at, so as you can see, the use of DNNs is very well motivated, because I think those of you who are familiar with multi-user detection are possibly familiar with the fact that the complexity involved in multi-user detection is very, very large, right? If you have to have alphabet size of S and K users, you have to search among S power K sets in order to perform ML detection, which is why ML detection is very, very difficult. But then you have suboptimum type of detectors, like, for example, the sphere decoders and so on, right? But the complexity is very high. Vita-B decoding will not be able to handle because the number of states will become very, very large when S and K are large. So we cannot implement a Vita-B decoder, but you can definitely implement a multi-user detector based on deep learning techniques for sure, right? Which is why the reason it's well motivated. In addition, if you exploit the structure that is present in the problem, right? You perform SIC type of structure, then you are by PIC based structure, you can decrease the complexity and use much less training in order to. Now, I will discuss over the air computation. I will discuss its application, right? So I think, let us see, I think we're running short of time. Over the air computation uses some kind of a NOMA principle. So what you're doing, you have a large number of sensors with transmitting data, and you want to take a weighted sum of the symbols, weighted sum of the measurements coming from many different sensors, right? What do you do? Normally, orthogonal multiple access, what do? You take the data from one center, you read it, go and next slot, you read the next one, and so on. And then you take a weighted sum. But that will require large K different time slots to be allocated to you, right? Or K different resource blocks. What you do instead, you allow all of them to transmit concurrently, right? How is this done? Suppose you take the channel to be HK between the IoT or a sensor node to the access point, and there are capital K of them. Suppose you want to do a weighted sum of the measurements, WK into XK. What you do is you intentionally transmit WK by HK into XK. You take the measurement, you don't transmit the measurement itself, but you transmit WK by HK. And when it passes through the channel HK, this gets cancelled out, it becomes WK into XK, and that is summed. So what is happening is computation is being performed in the air. So whatever the access point receives is the weighted sum that it wanted to compute. So computation is not done. So the advantage of this is that computation is done in the air. The second advantage is that you are using only one channel resource, one resource block in order to transmit from all the sensors at the same time, right? There's a lot of work on this, right? We're going to exploit this in cellular communication. I want to discuss one particular application where DNNs have been exploited in this particular scenario. Look at this. You have a central processing unit. You have many different access points here, and they are all attached to various. So there are capital K users in this network, right? There are so many access points, and then there is a central processing unit to which you are having data sent. So, and here I think there are says capital M access points and capital K users in a cell, right? So what is typically done? The conventional approach, let us look at it. Maybe if we talk about the notation first. I'm assuming the access points have capital N antennas, right? Once I complete this, the picture will be much clearer. The vector channel coefficients from at the mth access point from the kth user is HMK. It's a vector of channel coefficient because you have multiple antennas, right? Now, what will be the received signal at the mth access point? Because they have n antennas, it will be n-sized vector. It will be a weighted sum of signal emanating from all the k users. Okay, HMK with power pk you're transmitting from each user and sk. So what is the classical approach? I hope this is clear. Each access point has to decode the information coming from the k users and then transmit to the central processing unit. What is the disadvantage of this technique? Right? The disadvantage of these techniques is that you may be able to successfully decode some of these symbols, some of them will not be able to decode at the access point. Also, you will have to, many different access points may decode the symbol of one user. Maybe one user is in between two access points, and both of them may succeed in decoding, and they are going to transmit the same information multiple times to the central processing unit from the access point to the central processing unit. So this is very, very wasteful. Now, what is the classical approach? The classical approach is to take this wire, use zero forcing techniques or MRC. MRC means that you're doing mash filtering, right? You multiply with HMK Hermitian, and then you do detection and hard decoding, and then you try to detect SK. Or you use zero forcing in order to cancel out the interference and try to detect each one of these S1, S of capital K. Then you decode, estimate SK, decode it, re-encode it, and then transmit it from the access point to the central processing unit using orthogonal multiple access, one at a time. As you can see, this is very, very wasteful of channel resources, right? Because of redundancy and because of use of orthogonal multiple access. I hope you're able to appreciate what is going on. The users are transmitting, the information is available at various access points, right? And you try to decode the symbols coming from the various users. After decoding, you transmit it to the central processing unit using orthogonal, one at a time. This one transmits, then this one. Look at a different approach to this, right? The different approach would be that each access point, let us say, uses MRC. That means it's basically trying to do some kind of match filtering, right? Then it calculates some quantity called RMK. What is that RMK? It is simply a match filter output, HMK Hermitian into Y. I hope this is clear. See, each one of them, you simply apply HMK Hermitian into YM. Obviously, the stronger component will be SK with power PK. The rest of them will be diminished because you have multiple antennas and the channels are all approximately orthogonal. They'll be at least weakly orthogonal. So you will find that strong component will be SK and there will be interference. Right? Then you have this RMKs. So, but what you do, you quantize this RMK using alpha bits. Okay, and to get R tilde MK, that you transmit it, right? And you have so many access points, right? The mth access point transmits R tilde MK concurrently. That's very important. Over the air computation, we're going to compute, transmit R tilde MK, these bits. How many bits? Alpha bits, and going to transmit all of them concurrently at the central processing unit. You're going to get a weighted sum. Using this weighted sum, the CPU decodes SK and RK. That means you understand this step of signal. Suppose you don't quantize. then you're getting RMK. This one has a SK component dominating, the other one, and so on. So you'll have various users dominating. So for each user, you're transmitting the uplink. So just using K transmissions are able to transmit to the central processing unit. That means you're doing over-the-air computation using NOMA principles. Right? So redundant transmissions of symbols are avoided because each user is transmitting at the same time to the central processing unit. Right? For each user, you're going to transmit concurrently from each access point, and all the access points are transmitting concurrently. So you get this RK, and from the RK, you try to decode. Now, this RMK are obviously correlated quantities, and you know, redundant transmissions are avoided, but these RMKs are definitely correlated because the same symbol that's appearing in the kth user will also appear as interference in the, because each symbol might be present in the RMKs transmitted by different access point, because each access point might be having the same symbol. And in some cases, the symbol that you are interested in might also appear as interference in the other access point when you're looking at different RKs, right? So it means that there is correlation definitely between these RMKs. So now look at a different approach based on deep learning techniques. What you do, each access point has got YM, which is what that means when it looks at the information transmitted by all the users, you get YM. You know the channels HM1 to HMK to each of the K users, and PM, let us say, is the maximum power that you can allocate. You look at a certain mapping. Obviously, we're talking about functions here because I'm going to use deep learning techniques to fine-tune my function. For each user, for each access point. Each access point uses an FM function, right, which is optimized, and then you generate an AM. Then all these AMs that are computed are, you take a weighted, that means you're going to take a weighted combination of them. They're all going to transmit concurrently using various powers QM, and therefore the computation, at the CPU, what you receive is by over-the-air computation, you're going to get a sum, weighted sum. Okay. Now, what does the CPU do? It applies a certain function G to which, to the Z, and with the knowledge of Q1 to Q of M. By knowing these weights and by knowing the Z, it tries to decode all these symbols S1 tilde to SK tilde. S1 cap to SK cap. So as you can see, we have reframed the problem, and we used over-the-air computation, and we used deep neural networks. You'll also notice that what has been done here is something very unique. See, each access point is calculating based on what it has received. It is mapping it to a certain function AM. All these AMs are being transmitted concurrently with different weights. Does it not amount to one stage of a DNN, right? You're taking a weighted combination of the signals coming, right? It is like one stage of the DNN, right? So that is why it's interesting, right? This is like one stage. So what you do is you have one DNN at certain function here, then you have a weighted combination here, you have one more DNN at the CPU, and you fine tune all of these in order to detect the symbols directly. Okay. This is the basic idea. I think we're running short of time. Massive machine type communication, also there are very interesting problems related to DNS. The problem comes like this. You have an access point, a large number of IoT devices with various resource blocks allocated, but you will find that they can shoot data whenever they want, which means that some of them use the same power and the same resource blocks. It's impossible to decode them, and this information will be lost. And this is a collision. But if they transmit using the same resource block, but they use different powers, for example, this one is doing, right, using the Mmth resource block, but using different powers, then SIC can be used and it's able to decode each of them individually, right? So you have received power versus resource block, and you try to make sure that allocate them. In many cases, you cannot avoid collisions. Collisions will be there, the packet will be lost, and it has to retransmit. Right? This is the problem with grant-free access. And the reason why grant-free access is required also is explaining to you, right? Like in a typical communication, grant-based communication, it sends a sync signal, it sends this one, and then you get a preamble, then you get an array response, you get a connection request, a connection resolution, and repeats it till it's possible, then a data transmission, and then an acknowledgement. Right? In IoT devices, that all that is done away with. It sends a sync, and you automatically shoot data and wait for an acknowledgement. If it doesn't work, retransmit and wait for an acknowledgement. Right? So the overheads are reduced, signaling overheads are reduced, but some certain things become very, very important. You must know which user should be allowed to transmit and which user, how each user is battery operated, his battery is supposed to last 10 years, which means that, and it has a certain traffic pattern. So you can use DNNs in order to study these traffic patterns to make sure that you schedule these users in a sensible way, and so that you avoid these collisions to the maximum possible extent. Because packet loss does not just mean loss of time, it also means loss of energy, because 2 IoT nodes have wasted their energy, or 2 or more. Right? So DNNs are very, very useful in massive machine type communication. So the challenges in Mmtc, I think we're running short of time, I think are many. So I will skip these. DNNs can be used to select uplink users in semi-grant scheme. Which users should transmit on the uplink? If it is semi-grant, that means you're not allowing every user to just shoot data. You're allowing a certain subset of users. You can select which users can transmit uplink, what is the power that they can use, and so on. So that you minimize the chances of collision. If you can predict the data transmission by MTDs by monitoring the traffic patterns, even better than that. And how to ensure different quality of service for different category of traffic, because various IoT nodes might have different type of QoS. You have to make sure that you have DNNs, then you can take care of different quality of service. Right? DNNs can also be used, for example, in NOMA with caching. Suppose you have a base station at this is not a great figure, but it's a base station here. These content servers are here, right? So when people download data or click computer traffic and so on, most of the time they're looking at very common things that become very important at that particular point of time. Those files are important, right? So what is done is from the base station, you dump all the files in the important files that are being accessed very frequently to the content servers. And when the users require data, the content server directly serves them so that you don't request the base station to transmit, right? So the content server, this is called NOMA with caching, right? You're caching it in the content servers. So, but if you are able to predict, see, the amount of content servers don't have infinite amount of data that you can store, right? They want to have certain number of files that you can store. You have to decide which files are important, which are most likely to be accessed by users, depending by studying the traffic patterns, what people are accessing at that particular point of time, and then fill up your cache that you have here at the content servers with appropriate files, right? So this definitely can use DNNs in order if you want to ensure that the cache miss probability is minimized. One other example where DNNs can be very, very useful is intelligent reflecting surfaces, also called RIS, reconfigurable intelligent surfaces. Here, these are actually, metamaterials. Each one of these elements can be controlled. Its behavior can be controlled. For example, its phase. Suppose you have a certain signal impinging on it, it can reflect it with a certain phase, right? And amplitude. What happens then is that you can place these on walls, on buildings. And recently, Nippon has also made a transparent type of RIS, right, with various metamaterials which are also transparent, right? So it is just a glass pane, but it takes a signal from here. Each of these elements can tune the signal, can change the phase of the transmitted signal in such a way that is perfectly co-phased for, let us say, this user. So what's happened here is that you're able to change the propagation environment, right? So IRS, or intelligent reflecting surfaces, are very, very important, but you have a large number of elements, let us say 100 of them, and you're able to change the propagation environment, and you're able to strengthen the signal coming to one user. You're able to do some kind of beamforming and it is it's different from relaying, right? It is just a full duplex system, because whatever you transmit, it is reflected back with a phase. So the strength of the SNR at this particular user is very, very good. Right? Interestingly, this can also be used for NOMA. You can transmit to the IRS, which transmits to different users from different clusters concurrently using NOMA principles. DNNs are very useful here, because controlling the phases intelligently to transmit to maximum number of users definitely would require DNNs. Similarly, you have walls of various rooms. Suppose you have a building in which the various walls are controlled by these metamaterials. Then what happens is the propagation environment can be controlled. You can ensure that one particular wall will transmit a certain frequency band, but not the other frequency band. That way you can have Wi-Fi, let us say, in each of the rooms, and still they will not interfere with each other, right? But one of the other user requires this Wi-Fi, then he will be able to access it. It can be made transparent to that particular band. So as you can see, this requires huge amount of control, and that is only possible if DNNs are going to be used. But this is going to be the way 6G will be, because each wall, each building, you control the propagation environment in such a way to enhance communication. So this is the summary. I think as networks become more complex with the different kinds of traffics, different QoS, DNNs are going to be used, because it's otherwise impossible to actually deal with this optimization, right? You have to optimize transmissions for throughput, access probability, latency, node level energy efficiency, and system level energy efficiency. So all this will not be possible without DNNs. A network can be optimized as a whole instead of just trying to optimize each block. You're not trying to optimize a receiver or a transmitter. Your whole transceiver can be optimized if you use DNNs. We have seen one such example. And I also discussed one DNN and its application to caching. So you can reduce the amount of cache miss probability and reduce the time required to access a file. Right? And DNNs can also be used for practical non-idealities in circuits. For example, I don't know how many of you are familiar with IQ imbalance in RF circuits. Basically, you have the cos and the sine are not 90-degree apart, but a little bit less than 90, and the amplitudes are different. It happens when you implement a modulator on a chip, right? In such cases, DNNs can automatically take care of these non-idealities, so you don't have to worry about it, right? So this is the summary of what I had to say. If there are any questions I can take at this point.
Thank you very much, sir, for your valuable talk. Now I request our audience, if you have any questions, you can ask. Anyone is having any questions? You can unmute yourself, then ask. So I allow you to unmute yourself. So
otherwise, you can raise your hand if you have any questions.
Yeah. No, I unmute yourself. I allow you to unmute yourself. Please ask any question.
Can I ask one question, sir?
Yeah, please go ahead. Please go ahead. Yeah.
Actually, I am actually not in domain, so I am interested in this your presentation. This is very nice presentations, and this topic also a new topic. So
it's new to everybody. That is a point.
In 46 page, you just show that one diversity of the NOMA transmission systems. So
yeah, just hold on, please. Let me get that slide. Yeah,
46 page, I think. If I am not wrong, 46 page. There are diversity in NOMA transmission systems.
Okay.
So there you see that two mobile connections are transmitting with connection with the NOMA. So my question is, if the system, suppose that user is traveling from one BTS to another BTS.
Yeah.
So is there any effect in these transmission systems?
Effect of what?
Transmission system, suppose this BTS, that transmission or user depend on that same BTS. If that user changes from one station to another stations, means one BTS to another BTS, in moving, actually the customer is moving from
yes. This handoff, etc., is not something that I've considered at all. I assume that the users in the particular base station, they are fixed, and then we selected one as the near, one as the far. And we're trying to ensure that, see, we're not considered network level aspects at all. All we have done is to say that, well, people are focusing only on improving the performance of the far user. What we have done is try to improve the performance of the near user also by combining.
Okay.
Which makes sense because the power allocated to the far user can increase and its performance can again increase. It's an indirect way of doing things. And we're able to attain a diversity of 2 for the near user, which nobody has been able to do. That means we are also ensuring that the near user is gaining because of participating. If this near user does not participate, then the far user will have poor performance. But now what's happening is the near user also is gaining because of this participation. Otherwise, it will not get diversity. It will only get signal from the base station.
Okay, sir.
Yeah.
Thank you.
That is the point. But we are not definitely considered network level aspects. Yes.
Okay. Sir.
Yeah.
Thank you, sir.
So any other questions you have? Anyone having? You can unmute yourself. You can ask if you have any question. If you have no questions, we can stop it. So let's just thank again Professor Sankar Prakash sir for his valuable talk. On behalf of whole organizing committee, I thank you again, sir, for accepting our invitation and delivering this talk. So thank you very much, sir.
Thank you very much for your invite.
Happy
to join. Thank you. Bye.
All of you, please join the Google